Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Movellus with Vick. Going to talk today about distributed voltage frequency scaling. DVFS has been around for years. It's been used in the mobile market for a long time. What's changed now? Why now?
I think you're right that it has been used for years. What's changing now is the fact that this has been a technique that's deployed at the pointy end of the spear. It hasn't been broadly or more ubiquitously enabled because of the design challenges associated with it. But as energy becomes more and more of an important factor, these advanced techniques have to be more broadly deployed, and that's what we're seeing.
And everybody's sort of used to this as they start getting into the more advanced nodes too, right? In the past, when you were at 65 nanometers, you were thinking, okay, why do I ever need DVFS? But that's no longer the case.
Yeah, there's not a parameter available that isn't being pushed to the extreme. And so manipulating voltage and frequency to save power is really what the game is all about. There's a variety of techniques deployed. We'll be happy to walk through the specific details of DVFS and how to enable it.
Okay, let's take a look.
Sure.
Lee, what are we looking at?
Well, we're looking at quite the alphabet soup of modern power-saving techniques. So let me walk you through these, something that my wife doesn't let me do at parties, so I don't get to do this much. But in this context, it makes sense. There are a variety of techniques. Again, they're all about manipulating frequency or voltage in order to save power. Starting here with DFS, that's dynamic frequency scaling. Essentially, you're adjusting the frequency to accommodate the demand. If you need to run really fast, you put the frequency higher. If you need less frequency or less horsepower, then you can drop the frequency down. So it's manipulation of the frequency in order to save power. And there's a linear relationship. Remember, there's a V squared F relationship between voltage, frequency, and power. Linear is the power savings that you get from frequency scaling. As we move on to dynamic voltage scaling here, it's the same technique. You're manipulating the voltage. And remember, you're getting a quadratic improvement here. The difference is that DVS is a bit more complicated to deploy than just changing the frequency. And in fact, what we typically see is people not continuously monitoring or adjusting the voltage, but doing it in a discrete fashion. So you'll decide either at design time or on the tester a number of discrete steps, your DVFS states, and then you'll flip between those on the fly as part of your DVS solution. When you combine those two, that's where you get DVFS, where you're manipulating the frequency and the voltage, again, in a discrete level, and you're getting slightly better than quadratic power savings. This is really the target. People are trying to do everything they can to get more robust and more power efficient designs. And so this is the technique that they're deploying. And just to completeness and to round out the table, AVS is adaptive voltage scaling. Here, you're not doing it in a continuous or not doing it in a discrete fashion, but you're continuously manipulating the voltage in order to get savings. There is a quadratic savings to add here, but again, it's a much more complicated technique to deploy. So we're seeing people trying to migrate and deploying all of these across their designs. DVFS is more typically the target. The other thing that we're seeing is that these techniques can be deployed either not at all, sadly, which is where we're at today, at the entire chip level, or at a per core or per cluster level. The more granular the designs, the greater the power savings.
Is all this just due to the fact that you're now doing more computing of more data?
It is. It's absolutely driven by the scope, right? The number of CPUs, multi-core systems are much more common. The GPU have an array of compute elements. AI has typically a matrix or an array of compute elements, be they small max or larger engines. It's that complexity and the scale of those that's driving the need to manipulate these on a more localized basis. Otherwise, your entire chip is suffering for a case where you're trying to find the least common denominator, and that really cripples the ability to save power.
Years ago, DVFS was limited to a very elite group of engineers. Has this changed? Is it now becoming more common?
It is on the way to becoming more common, and in fact, I would argue it has to. We're certainly seeing customers trending in that direction. There's two reasons for that. One is the inevitable demand. The demand from marketing, the demand from customers, the demand for end users to have a better user experience, more battery life. The other thing is we're seeing is just the design complexity and the enablement. Some of the techniques that required to deploy these have been onerous in the past, and the domain of the elite. Those are now becoming much more broadly deployed, and the enabling factor is what's really driving a lot of the migration that we're seeing.
There's also much higher utilization of whatever processing elements are in a design. So as a result of that, you really need to control the power too, right? Your power budget doesn't change, but the amount of computing that you have to do is changing.
Absolutely. And The way to think of this is it can drive both increases in performance and also savings in energy. How you deploy it depends upon your particular needs. Throttling is something that's existed in phones and laptops for a long time, where you run the voltage and the frequency as high as possible, then you run into some thermal limits and you have to be able to manipulate that. That's how you get the maximum performance level. The way you get the maximum battery life is that you turn everything down to as quiescent a state as possible to save power. That dynamic manipulation across frequency, which is linear, and voltage, which is quadratic, is where you get these savings, and that's what people are starting to deploy.
One of the challenges as you do this, though, as you particularly turn down the voltage, is that your noise level becomes much more sensitive. All your tolerances are much tighter as you turn down the voltage. Any noise that comes in here causes problems. How does this work with this?
That's absolutely true. And in fact, I would argue that the power grid design of a modern SoC, especially a larger design, is an incredibly complicated endeavor because of the demands of chiplets, the scale of the designs, the modularity, the rapidly changing workloads. It creates a very hostile environment. So having the ability to create this localized control, having the ability to isolate certain regions with power islands in a simple manner, as opposed to some of the more complicated techniques, is an enabler that drives this technology forward.
So now that you're trying to move this down to the mainstream designs, what do you have to worry about that you didn't have to worry about before, and where do people go wrong?
Well, I think one of the key things is that in order to enable this kind of power techniques, you have to consider a case where you're driving your voltage manipulation, in particular, from an external to an internal factor. In other words, we're talking about on-die voltage regulation. Because if you have an array of 32 compute elements, putting 32 external voltage regulators on a board is just simply prohibitive because of cost and routing and other issues. So driving those into the designs and having a small enough or digital technology that allows you to embed those inside your design is an enabler that they didn't have in the past. So they were sort of struggling for the techniques to allow this without having to be really esoteric in terms of the design approach.
Is this going to be a transition? We're going from DVS to DVFS to AVS, or is it now going to say DVFS is where we stop?
I think DVFS is probably the target for most people. It's that combination of voltage and frequency scaling. That's really where you want to be, and you can manipulate both. And there are slightly different time scales. You can change frequency faster than you can change voltage. And how fast you can make that change is also a key enabler for the different power optimization states. Ultimately, yeah, a more adaptive voltage and frequency scaling would be the ideal, and we'll get to that point. But I think first we have to more broadly deploy these techniques, allow everyone to take advantage of them, and leverage that. And again, it can be done at the chip level or more granular. And the more granular you go, the more power savings. And I can demonstrate how that works.
Lee, how does all this work?
We talked about the concept of taking things from the chip level down to the core level. Let me walk you through how that works. So what we have here is a system with some number of compute elements. This can be an array of processing cores or clusters within an AI engine. And when the power grid is designed, it has to be designed to meet the performance level that the customer demands, that marketing then demands, and the bosses demand. So you have to be able to design your power grid to take the worst case scenario of every core running absolutely flat out. And that's the design parameter. If you don't have the ability to manipulate that voltage, it's stuck there. So this is a snapshot in time at some point in the future where you're not needing every core to be running flat out. In fact, the workload demands across these is varying. So what happens is all of this energy is just wasted. And that's a problem. It impacts reliability, causes thermal issues. This is not what you want. It's not an optimized design. But if you don't have the ability to manipulate the voltage, you're stuck. The next level is per chip. If I have the ability to manipulate the voltage at the chip level, I can bring it down to the highest demand or the minimum of the highest demands. What I mean by that is this is the worst case workload at this particular moment in time. I have to give it enough voltage. So I can drop this voltage down to this level, which is what I need, plus a little bit of margin. And the savings that you get from that is all of this. So you can see there are savings to be had even at the chip level by deploying just the voltage scaling at the chip level. And there are studies that show meaningful improvement. Beyond that is where it gets really interesting.
You've got a lot of moving pieces here, though, right? You've got different workloads, you've got different applications, and potentially you have completely different chiplets and cores working here.
Correct. And that's why the ability to manipulate these locally and to command them with your software infrastructure in a simple and straightforward manner is key. But once you have that, once you have the ability to embed localized voltage regulation that gives you the ability to manipulate them, the savings is significant. And that's why people are going through this, because if we can move from a world where It's the worst case or the lowest common denominator to a world where the voltage is set on a per core basis. Now the energy savings are even more dramatic. This is what people are really looking for. They really want that ability to more finely control, and the more fine control it is, the better the savings.
This also allows you to do things like thermal management too, right? Because now you may have one core that's running hot. Okay, we need to move this over and distribute some of the load.
That's a great point. I've been talking here about things that are entirely workload based, and certainly under software control you can drive this, but that doesn't have to be the only factor. And in fact, in the real world, they're often not. Thermal demands, system demands, chiplet constraint interfaces, all those will drive where and how you manipulate the voltage, spread the load. And in fact, in the 3D world, you may have devices that are on top of each other, so you have to be spatially aware as well as temporally aware. The other thing that I haven't drawn here is that the more quickly you can manipulate the voltage up and down, the more rapidly you can go in and out of these power states, and the more power savings can be had.
How do you get that feedback to know exactly what's happening on each one of these cores and what you need to manipulate in terms of the voltage?
Well, that's a challenge. I think we've seen in the industry over the past few years a drive towards more of a world where we're sensing what's happening. You know, you wouldn't build an oven without a little window on it. You wouldn't back up without looking in your rearview mirror. Similarly, designs have tended to be very closed loop. You design it and then you hope it works. Now we're seeing more embedded sensors. Those sensors are driving data that feeds the analytics engines of silicon lifecycle management. The ability to see inside your power grid to see what's happening, and these embedded voltage regulators can also provide that telemetry, is a key aspect of understanding what to do and when to do it.
You also don't have the margin that you used to have in the past. And you see some of the large designs that are going on by the systems companies, something like 45% of all the leading edge designs. They're working with very narrow margins. What do they do here? What changes here that didn't happen in the past?
Yeah, those margins are razor thin. And because of that, the demands on the power grid are really key. So we typically see customers deploy one of two techniques. The first is they will over provision their voltage because they don't want to be able to have a design that's capable of failing. In other words, they will over provision, they will over margin to make sure that if there were any droops or any excursions in their power grid, it'll never get to the point where they'll experience a failure. That's fine, but again, going back to the customers and the marketing folks who are always pushing the parameters, giving up that much performance used to be an option. It's just not anymore. So we're seeing more and more customers at that ragged edge of what they're doing, where they're designing a system to work most of the time, and then they're deploying droop mitigation or other techniques to catch those excursions and to be able to respond, whether that's through DVFS or droop mitigation, the frequency, whatever you do, that has to be a part of the design, and that's done at the very beginning where you design that flexibility in, because it's really difficult to do later.
What happened to some of these cores' age? They don't necessarily behave the way that they were expected to when they first came out. Plus, you also have variations even within the same type of core, homogeneous cores. As they're produced, they may not be at exactly the same speed, power, utilization. Each one is going to be a little bit different.
Yeah, that's exactly right. I think you hit on two fundamental points that are critical to understand here. The first is aging, right? Where we know over time, just like I need more coffee in the morning, as transistors age, they're going to need a little bit of help as they go through the design. So you typically design with a little bit of extra margin because you know 10 years from now, you're going to need some level of voltage to be able to service that aging transistor. But I don't need that at day zero. I don't need it at day one, which means all of this is wasted power and energy and reduced reliability and more thermal stress. So having the ability to manipulate this and age gradually, bring that voltage up over time is key. The other, as you described, is these are not unique. They're not identical, right? There is variation, process variation, workload variation, aging variation across these devices. So being able to localize that aging control is a key factor.
So this becomes the great leveler for you, right?
So to speak, yeah. The local manipulation of voltage allows you to handle the dynamic changing environment over time, whether it's short-term thermal impact or long-term aging impact. This flexibility is a critical factor.
So all this looks really great on a whiteboard. What does it take to enable it?
Yeah, it's, again, this is not something that's been broadly deployed because of the challenges. We talked about you can't have multiple external regulators. You've got to bring them on the die. When you bring them on the die, they have to be small because you're embedding them, again, in amongst your digital array or digital compute blocks. They need to be very fast, much faster than external regulators, smaller than in traditional techniques. They have to provide that observability that I was talking about, and they have to be flexible from a firmware perspective so that you can adjust for aging or for changing workload demands. All those requirements have made it a very difficult environment until more recent changes in the market. So now we're starting to see the enabling technologies come out.
You know, when you look at this, you think about LDOs, and LDOs have been out there for a long time. Why haven't they been used here?
The reason is applicability. So if you think about an LDO, typically they're designed to provide a low amount of current to a small specialized piece of circuitry with high noise suppression. You're talking about currents in the order of hundreds of milliamps. Here, because we're driving the voltage per core or per cluster, we're talking about currents in the amp ranges. So they just typically don't apply. They're not quite the right solution. Once we have the ability to drive higher currents and still do the local manipulation, then this technology becomes applicable and really exciting to allow customers this degree of freedom.
Vick, thanks for a great explanation.
My pleasure.